Hi, everyone, and welcome to this talk. It's the last talk before lunch, so that's always nice. But yeah, today I'm going to be talking about graph machine learning and just a little bit about myself. I am an AI scientist, which is just a glorified data scientist at Intuit. I work in the trust and safety domain, and we build fraud detection models to prevent bad actor abuse of Intuit products. Before that, I was working on time series forecasting, anomaly detection, and prior to Intuit, I was a data scientist at GoDaddy, where I was working on a lot of deep learning, NLP models, recommendation models. So my background has pretty much been in traditional machine learning and a little bit of deep learning. And while I'm not a first-time speaker, I have spoken at Pyohio before, but that was a virtual one. But this is the first in-person conference in a while, and that's amazing. I live in SF. Yeah, I live in SF, but I actually just recently moved to the city. It's been amazing. And I'm interested in general in a lot of things. When people talk about their passions, it's like something they've been doing for a lot of time. With me, I think my hobbies come and go within a span of months. Like at one point, I was interested in origami. This is one of my creations from 30 Days of Origami. I was interested in backpacking. I did it twice, and I really got tired of it. Hiking like 10 miles, picking up 20 kgs on your back is not fun. This is me posing with the uke, but I do actually know how to play it. But yeah, so one of the things that also I got into and didn't really stick with it a lot was graph machine learning. So this talk isn't about how I became an expert. It's just about my learnings as someone coming from the traditional deep learning background and how they got started with graphs. And the story about this is that I was working at Intuit, and one of the teams that I was working with had their data structured as a graph, right? And they came and they wanted to explore machine learning on this. Now, I had no background in graphs, but one of the first questions that I also had was, why do we even want this? And the only answer they had at the time was, well, we already have this graph in a database, right? It's structured, so why not just explore something? Well, I took it as a learning opportunity, and so that's what this talk is about. But I think if you've ever taken like a data structures algorithm class, you know what graphs are. But basically everything around you in real life, right? Anything that has relational structure to it can be converted to graphs. A simple one-dimensional text form, like a sentence, can be converted to a graph using the words as nodes. And if each word follows the previous one, you can assume that they have an edge in between them. This is an example of scene understanding, which is used in computer vision, right? And instead of just having more traditional sort of simple graphs, what this shows is that it's a scene where Daniel and Johnny are fighting one another. There's a referee. There's guys watching them, there's the audience, and the audience is watching everything. And apparently, Johnny and Daniel are levitating or standing over the mat, right? But you can have each object in this scene as a node, and as you can see, the nodes are not of the same type, right? They're not just people, they're not just a single individual. It can be an object, it can be a person. And the edges over here are also different. The referee is watching, whereas Johnny and Daniel are standing over the mat, right? So edges have different meanings. And that's what graphs are all about. You can actually assign intuitive meanings to your graph, which is just basically nodes and edges. All right, so how do we go from here to machine learning, right? At a very simple level, let's consider you have just a single node. It in itself is a graph. And one of the things you can do is try to classify this node into certain given classes. Or you can take a property or a feature of a node and try to predict it. At the edge level, you can predict if two nodes are going to have an edge between them. So what is the probability of it, right? And at a certain bigger level, you have subgraphs or even a single bigger graph, right? So think of proteins, molecules, you're trying to classify them. So that's graph classification. But in this talk, we're going to restrict ourselves to this application, which is link prediction. And for this example, just assume you've built like an amazing payments product or something, right? You have good actors, good customers, paying customers, but you also have certain fraudsters using your product, right? And you want to predict if this fraudster, for example, is going to interact with either the good customer or the bad customer, right? So ideally, what you want to do is predict an edge between two nodes. And that's what link prediction is all about. But yeah, OK. So let's get right into it. Let's talk about the math. Well, actually, no. That's not what this talk is about. This would take hours and hours, and I'm sure there are much better professors who've had lectures and presentations on this, so I will leave it to them. But what this talk is about is having an intuition. And so if you're someone who really enjoys the math and is getting started with graphs, I have a list of references. You can also find this by the link at the end. But yeah, so let's build intuition about graphs, right? So graph in general have nodes and edges. And we cannot go about talking this without talking about neighborhoods. So in this case, one term I do want to introduce here is k-hop neighborhoods, which is that if you take a node and you can hop around by one jump around it, it's called a one-hop neighborhood, right? And so you can imagine as you hop around from a given node to other nodes, you can build bigger and bigger neighborhoods. And why that is important is because we're going to talk about message passing. The assumption over here is that if you have an edge connecting nodes, it means that they have certain similarities between them, right? They share certain features. They have certain behaviors that are common to those two nodes. And when I first heard about message passing, I think the first thing that came to my mind was how, as a kid, if you had a secret and you would go and tell 5 of your friends, and they would go, and I didn't know it at that time, but they would go and tell 5 of their best friends. And apparently, you would get to know that information travels when the teacher was pulling you out and then asking you not to gossip. And so this is what happens, right? In a graph, information is supposed to travel. And the way it travels is through edges. So this is just a screenshot from this paper of GraphSage. We will use this neural network in the rest of the presentation. But essentially what they're doing over here, right, is they're taking neighborhoods of nodes. So let's consider this red node right here. You have a one-hop neighborhood, which is just all the nodes that are encircled here, right? And then you have 2 node neighborhoods and so on, like bigger and bigger neighborhoods. But if information is traveling through edges, it means you are going to, as a node, you're going to get information from 5 different nodes or 10 different nodes, right? And this can be a lot. So how do you aggregate it? Like, for example, if I had 5 friends coming and telling me their own gossip, I could probably concatenate it. I could probably take the maximum interesting message out of it, or I could probably just average it out. And so in mathematical terms, that's exactly what we do. If we assume that each node has something to tell us, and that's usually encoded in an array or a vector, then I can aggregate it using mean or max or some sort of a network as well. And the reason why this is important is because I'm building up to embeddings, right? So embeddings are what you get at the end of the training of a graph neural network, or any graph model, basically. And using this embedding, which we get for each node in the graph, or even each edge, and at an overall level, you can also possibly get it for the entire graph. If you have this embedding, you can use it to predict for your end task. You can build a node classifier for a single node. If you have 2 nodes and you want to predict an edge between them, you can look at both of their embeddings, and you can see if these embeddings are close enough in some dimensional space, And if they have very less distance, it's likely that they have an edge between them. And what this also means in that case is that two nodes that are connected via an edge are also going to have very similar embeddings. In link prediction, you can have two different tasks. So you can just have a simple link prediction, which is binary. But you can also have a weight. So imagine if your edge had a weight, and you had to predict it. And this is exactly what we're going to be taking as the example. OK, so far, we've talked a lot about like the theory of it. But let's move on to the example. And we're going to take movie recommendations as the case study. We're using deep graph library, so DGL. It basically does exactly what it says. It's a Python library built to help you make deep neural networks on graphs. And it abstracts away all the hardware and, I guess, the framework part of it. So if you're building a graph neural network over GPU or CPUs, or you're building it in PyTorch or TensorFlow, they have components that basically you can abstract. So you can just pick and use it and build a custom neural network. All right. And so a little bit about what we're going to talk about next. So this is the data set. We're going to take users. And these users have rated movies, right? So there are about 940 users. They've rated about 1,700 movies for a total of 100K. So this is a really small data set. So in total, we have 100,000 ratings. And as you can see, not every user has rated every movie, right? But our task here is going to be to predict what a user will rate a given movie, right? And how we can think of it as recommendation is, let's say this user comes to this website, and they tell us historically they've rated or they've liked such and such movies. And based on that, we can recommend what movies they should watch next. So what we're going to think about this is, if we predict a high rating for a user and a movie they haven't watched, we're going to recommend it to them. All right, so let's think about structuring our graph. Now, this is really small, and I'm going to zoom in a little bit. But here, we've taken all the users and the movies as our nodes. So again, there is no single type of node. There are, even at this point, there are two types of nodes. And for example, this user, right? User 650 has rated this movie Goodfellas with a rating of 4, which is our edge weight. This movie Babe, and also Twister with a rating of 4 again. So that's how our graph looks like at this point. It's very, very simple. And yeah, again, so far we've talked about the data set, but let's get right into the code. And so let's start with using DGL and building a custom neural network. So what we've done over here is we've started extending this PyTorch module. And initially, let's assume that we are only using the graph topology, right? So just nodes and edges to create an embedding. We assume that the user node and the movie node has certain embedding. But how do we actually pass information, right? So the magic really happens here. We are going to add these Sage convolutional layers, which is the paper that I just showed, Graph Sage. They have a new algorithm. I mean, not a new algorithm at this point, but they basically introduced an algorithm that aggregated information using a sample of neighbors in a neighborhood. And this is what we're going to use. Again, it's a convolutional layer. But if you're familiar with neural networks, this will look pretty familiar. But essentially, what we want to do over here, right, is take the either the user node or the movie node, and then we're going to pass information and aggregate it. So if we have a lot of information, the way we're going to aggregate this is using this function, aggregator type mean. Again, there are multiple ones. You can pick and choose the ones available in DGL. And that's our message passing. But how do we actually go from passing messages to building a recommendation model, right? So we're training embeddings, but going from embeddings to an actual recommendation or a rating prediction task, you need another network or another layer, right? So I have another smaller network here. I think this can be pretty much anything, so we don't really care about all that is here. But what's important is this. We're going to take both, so the input dimension over here is embedding dimension into 2, and that's because we're going to take both user and movie embedding, right? And we want to calculate what the rating is going to be. So the output dimension of this network is just going to be this, which is a singular value. It's basically a scalar. And so yeah, so basically just going from all the embeddings to your final rating, which is just a single scalar. But so far, we've talked about learning from the graph. It has nodes and it has edges, but we're still learning only from the topology, right? We still haven't added any user or movie features, right? So let's say you have a user and we have their age, we have their gender, occupation, and so on, right? For a movie, we have their what year the movie was released in, we have what genre the movie is of, right? And it is important because in a typical machine learning system, we learn not just from, I guess, similar users, but the way we define similar users is using the features, right? So how do we add that as part of the GNN? And so once we have these features, we can take it as part of our neural network, right? So here, the in features can be anything, either your user or your movie. And then you basically assume the input, the first input that your model will see are these features, and then you continue on with any of the convolutions. But there's another way. So instead of adding all of this feature data as a matrix to your model, the other way that you can actually add more information is by changing the topology. So let's say you decide that for all the categorical features you have, you build nodes, right? So for the user, for example, for their occupation, which is categorical, you have a different node. And in this example, user 143 is a programmer, so we have an edge between them. And similarly, for a movie, if there is a particular genre that movie is of, you have edges going from the movie to that genre. So we've talked about 2 ways to add features to our graph model, right? But what is the difference between them? So in the first case, we're adding this matrix information directly to the graph model. And in the second case, we're changing the topology to have more nodes or have categorical feature nodes in the graph structure. In the first case, if you're adding information directly, it's usually good for dense and continuous features. As we know, neural networks are not very good with sparse data. And because you have fewer nodes, because typically you're just adding a matrix to your model, you're not adding more nodes or edges, you have fewer nodes to compute embeddings for, so it is efficient. And in general, if you're coming from a more traditional background, you may have data that is already structured like a table. So you have user features and you have movie features and a specific table. It's just easier to use them directly as part of your GNN. However, in the other case, so if you have a lot of sparse and categorical features, like, for example, if you have genre of a movie, or if you have the state the user belongs to, you can use nodes to represent them. It's also more interpretable. What I mean by that is, let's say you were trying to explain to your to someone using your model, right, why this prediction has been made. You can say that this user is a programmer, and in general, we've seen programmers like action movies, for example. That's not a stereotype I'm making, that's just an example. But so far, we've skipped one of the more common machine learning tasks, which is how do we actually split train and test, right? So this is actually pretty similar to how we split in common traditional machine learning. So you can, if you have your data, you usually split it randomly or using some temporal features, for example, taking 80% of the data, of the older data as historical, as the training data, and 20%, which is the most recent, for testing, right? You can do that here. But just one thing is very different, is that you assume that the graph nodes that you send to both training and testing are the same. So you assume all the movies and all the users, in our case, are the same in both training and testing. It's only the edges, because it's a link prediction task, that have changed in both the train and test. So in this function, for example, all I'm doing is taking a user and all the movies they've rated, right? And 20% of all the movies they've rated more recently as the test, and the rest is train. And so far we've defined it all in an abstract manner, but let's actually start passing some information from data frames, right? So if you have a pandas data frame, or basically any sort of tabular data, right? You want to create a graph out of it that you can actually pass to the model. And this is what we do here. Ratings DF is just a singular data frame that has all the movies that users have rated. So each row over here is a movie that a user has rated. You get the user and movie nodes, and then you basically just define the edges, which are user to movie. And this, if you're wondering about why we're adding number of users over here, is just a neat trick for indexing. But essentially, what we're trying to do over here is just create a graph. So you pass all the source and destination nodes to this DGL initializer, and there's your graph. We create both training and testing graphs separately, right? And then we start training the model. So as goes with most neural networks, you're going to use some sort of a optimizer and a loss function, right? In our case, we are using, over here, you see mean squared error loss, because we're trying to predict a rating. And a rating is from 1 to 5 in this case, and it has a monotonicity associated with it, so you can think of it as a continuous variable. But yeah, so in general, if you're using this framework, right, we used a regression metric, and we used mean square error and RMSE for the loss function. But if you're using, if you want to predict the binary existence, whether the edge exists or not, you can use classification metrics, right? And for that, you will pretty much use the binary cross entropy loss if it's a binary system. And in general, recommendation, because recommendation models have different metrics we evaluate with, you can choose hit set k. Hit set k is basically how many out of the top recommendations are actually accurate. So in this case, it would be out of how many movies we recommend, the user has actually rated them as high. But yeah, and precision and mean average precision are just other common metrics. But I think this is the most interesting part. So coming in from someone who hadn't really heard of graph machine learning before, these are some of the things that I learned. OK, so if you have a graph, you can have different types of nodes and edges, like we saw even in this example, right? In the case of, and homogeneous just means you have a single type of node and a single type of edge, whereas heterogeneous means your nodes and edges have different meanings. It can be you're trying to predict just a single type of edge, right? So in our case, if there was an edge going from a movie to their genre, right? We actually don't want to predict that edge because we're only interested in the user to movie edge. So in case you're using this, make sure your training loop includes only the edges that you want to predict. In recommendation systems especially, it is important to specify both positive and negative examples, right? In a lot of cases, though, that isn't really possible. So let's take the case of Amazon, or just basically any e-commerce website, right? You go to Amazon and you try to search for kids' pianos, and you see a bunch of results. Let's say you like this one, and then you click on it, right? Now, that itself, like a click, is a positive feedback in our system, but just because you viewed all of this doesn't really mean that you actually went in and rated these as negative, right? However, we can really make assumptions and say that anything that you viewed before this is probably an implicit negative feedback. So why this is important is because we want to make sure that our model has both positive and negative data. And the way to create this in graphs is we already have edges, right? So for a link prediction task, we're trying to predict which nodes are likely to have an edge. But equally likely is if we know which edges do not exist at all and are not likely to exist in the future, right? So this is an example from the DGL documentation itself. And here they make that assumption. So basically, any edge that doesn't exist in the graph can be taken as a negative edge. But that may not be true in a lot of cases, right? So for your recommendation task, just because there is not a rating from a user to a movie doesn't mean that they would likely rate it as negative. So this is just something to be careful of. In a lot of cases, it is important to have or to know of assumptions that we have while training models, right? So transductive means if your nodes and your edges are pretty much going to, not the edges, but your nodes are pretty much going to remain the same. So if you have a lot of new nodes that are coming in real time, like new users or movies, you likely want to have this inductive training framework. And the reason I mention this is because the literature is very different for both of them. And if you have some static sort of system, which is pretty much going to stay the same, and you can do with like a 3-month or a 6-month retraining schedule, then it's probably just fine to use transductive. One thing which I learned one thing which is pretty interesting is that, let's say you do decide to have convolutional layers, right? The number of convolutional layers depends and actually defines on how many hop neighborhoods you're trying to go to. So let's say you do have 3 or 4 convolutional layers. It means you're going to hop over for each node to 4 hops, and then so you're going to get a lot bigger graph in this case, right? And let's say you have very, very few nodes, right? Your graph is really small. In that case, you're basically asking every node to consider all the nodes in the graph, which dilutes the information in each node, and that can lead to very less discriminative power. So if you have a smaller graph, make sure not to use a lot of convolutional layers, which is basically very similar to how we think about overfitting in machine learning. But yeah, I think the last one which I learned is, well, beware of black box frameworks. Graph machine learning is pretty new. There isn't a lot of documented applications, especially in the industry, right? So if you're working with a black box framework, make sure to know about all the implementation details for how the train test data is split, for how you're making predictions on that model. Because I face like a really huge data leakage issue where I would train a model for all sorts of data samples, and I would just get 100% accuracy every time. Perfect in a real scenario, but really scary if you're a seasoned data scientist. But yeah, so this was my talk. I hope you got something out of it. And so this is the link for getting all the materials. And yeah, that's my LinkedIn. And I'll be here outside if you have any questions. Thank you.